started yet. Do me a favor and open up your Chromebook. What, in this class? You always tell us to shut them. All right, go ahead and open up your Chromebook and then go to Wikipedia. Just type in Wikipedia. It makes all the sense in the world. Your job is to have your Chromebook ready and actually in functioning condition, or else. That's on the website. Okay, and then go. No, it's on. Just be quiet for a second. All right. Shh. 6 hour. It's not fifth, believe it or not. All right. Yeah. Go to graph theory. Just type that in. All right. Now, while you're doing that, it's going to come up real fast. Light, speed of light. And I'm going to hopefully pull up the website successfully myself. Oh, there's your pictures on the internet. Probably could get sued. Okay, is this page comes up. Now, the reason I did this, just try to pay attention. Here's a good thing. If you hated Chapter 4, didn't do well, Chapter 6 has nothing to do with it. And you're going to find that out probably in this book throughout the whole year. We're just getting you a smattering of different mathematical concepts that happen in the world. So when I opened up this chapter and I looked at, the notes from the old teacher and tried to figure this out, I asked why. So I went on YouTube first and tried to find a video about routes and networks. That's what I think the label of our chapter is. And the only thing I got was computer guys talking about routers. Anyone ever hear of a router? Yeah. So I think that's a router in our room right now. They call it a hub or something like that. But a router routes your computer to traffic out in the internet to go to, whatever, websites or what have you. I'm not saying I'm a computer guy. But they were too technical. And they were about fixing routing problems, and that was not what we were doing. But then what I thought is I got to find something that has, what is the connection, what we're doing. So I found this page. And, of course, Wikipedia, trustworthy or not, it's usually pretty good. I want you to go down just to the application part and just read those first two sentences. First two paragraphs. So go ahead and do that real quick, and then we'll talk about it. The only thing I really want you to get out of that is just some of the things that are listed. You could go back up to the top of the page. I read up to the top all the way down to halfway through the applications. I thought, okay, this is good just to put the student's mind in the right spot for what we're doing. But the rest of it, it's all pretty good as well, and it's talked about in our book a little bit. Euler, when you open up the beginning of the chapter, Euler, they do two little histories of a person. One of them's Euler, fascinating mathematician, but that's beside the point. What I want you to understand is, what we're going to be doing on a piece of paper is doing these connections, these web links or whatever, with vertices and edges. I'm thinking of our names here, and it's not going to be as complicated as what you see off to the right here, but this is how things are connected in the real world, maybe on the web or, some sort of other situation. And the thing that I thought about is you guys. You guys all have, what did I make you open up to start off? The Chromebook, okay? Where's your Chromebook connected to make it work? I actually pointed to it today. The only reason we can go to Wikipedia is because of that router or that whatever they call it, a hub or whatever. Where's that hub connected to? Probably the tech office, all right? And the tech office has something there. Where's the tech office connected to? I don't know how the web works. It might be a cell tower or something. I don't know if it's a cell tower, probably not. But that's connected to something else. These are all connections that we can write on a piece of paper. I'll tell you what, right now, your Chromebook will not work if this hub is broken. And it happens a lot, actually, that this hub doesn't work quite efficiently. If that does not work and that link is broken, you cannot go on the internet. All right? And that's what we're going to draw on a piece of paper. Everything that I'm going to do on this, I'm going to talk about it in terms of your Chromebook and how it's connected out to the real world and the internet. So, with all that being said, the more you read about that website, the more you might understand what we're doing today. Okay, a little bit. So that's why I put that link there. Then we can get into our terms. So you can put your Chromebooks away now. Now I'm getting suspicious. Because what are you doing? All right. So routing problems, not issues. Routing like examples, I guess, would be a better way of saying this. We have a network here, Lockport network. You're connected to that network. Consists of destinations with their connecting links. So I don't have to read these. You could write these. Reason I'm reading it is your Chromebook, which, sir, put that away before I put it away for you. I'm serious. I have a smile on my face, but I'm coming. Okay. All right. Consists of that. So your Chromebook is directly connected to this hub in our room. And then this hub probably goes to the tech office, and then the tech office. You know when you walk down the halls and your Chromebook's on, and you stay on the internet, you lose connection with one hub, but then you connect immediately to another one. Did you know that? Right. So these are all over the building, and some I think work more efficiently than others. But that's just me. Graph theory, there's that name Euler. Don't worry about it today. The study of Euler circuit problems and other routing problems. That's why I looked up graph theory on Wikipedia to try to see where the real world connections of those are. And there's certainly more than just this computer idea, but I think we all can handle that one and grasp that one. And what we're going to do is a graph. And they're not going to be complicated as far as, connected to how your computer connects to the internet and the outside world. But it's a collection of points, which shall be called vertices from now on, and the connections between them, which shall now be henceforth called edges. Can everyone say vertices and edges? Do you hear them? They sound so excited. Okay. So here's just a drawing. V stands for vertice or vertex. V, edge V. First V, call this like your Chromebook. Second V is the hub in our room. You have a direct connection to that hub, and then from there, some things happen. But there's just one simple connection. Doesn't have to be a line. We could do any kind of squiggly we want to make a direct connection from one vertex to another. This is wild. This is the next thing I looked up on Wikipedia because your book didn't explain this. So I had to go out and find out about a loop. Now, I'm not going to say I understand what a loop is. I've heard things that loop. You get stuck in a loop, but an edge, a vertex can be connected to itself. That's called a loop. What I had to look up is a term later about loops. There's something weird about them I didn't quite get. Okay, do this drawing, and this is not an emulation of what you're going to be doing for your homework. This is just, here is maybe a network. I don't know if I'm using that word correctly, but just understand maybe what I just said. A is your Chromebook. B is the what? Come on, what's the B? I've said it 5 times today. Starts with an H. The hub. Maybe it is a router. C would be the what? I just used this term. I just used it in the last example. LTO, what does that stand for? Lockport Tech Office. And then after that, the tech office sends you to D, and then D sends you to E. I don't know. Just trying to get you a feel for what this drawing actually represents. Okay, it's some sort of connection how A gets to E. And that's got to go through B, C, and D to get to E. What you need to understand is, when you're doing these drawings, it's almost impossible at times not to have them cross. So when these lines cross, it's because I can't possibly not have them cross because there's so many vertices. This is not a vertex. And the best way I can explain this is what I read directly out of your book. The best way to think of this is a bridge. If you were looking above as a bird or in a plane, you may not notice that that's a bridge and it may look like it's an intersection. Is a bridge going over a road an intersection, yes or no? No, it is not, sir. It is far from an intersection. Okay, so we did not get that one right. Now, this is an emulation of what your homework might look like. So this would be question number 1, or we'll call this officially example number 1, which is, what are we going to have to do about this? Okay, well, it actually isn't. It's right here. I just noticed it was already written. The first thing's a term. My bad, dogs. Roof. Adjacent vertices are 2 vertices connected by an edge. All right, the word adjacent. Always meant to be. I said I did say this last hour. I have triangle ABCD, and no one picked up on it. Could ABCD be a triangle? No. So I did say that mistake. Then they flipped me off. All right. Now, what vertex is adjacent to B? What vertex or vertices are adjacent to B in this simple drawing? A and what? C. And we use that term because, like in parallelograms, adjacent angles are supplementary. So we used that word before, adjacent. That's all I'm trying to get you to understand. So I don't think adjacent's a big word to understand. So adjacent vertices are two vertices connected by an edge. So the example that you might have to do in your homework is list the adjacent vertices. The smartest way to do this is to go in a nice little order. Who do you think the first one is what we're going to start with? Letter A. Who is A adjacent to? Is A adjacent to B, yes or no? Oh yeah, so A and B are. Is A adjacent to C, yes or no? Direct line. Is A adjacent to D? I couldn't think of the next letter in the alphabet. Is it, yes or no? And then E, yes? So redonkulous. A is connected to all of them directly by one link. Now we move to B. Am I going to say B is connected to A, or has that already been established? It's already been established. So who else is B directly connected to? C. Anyone else? So B is connected to C and A, which has already been established. It's not directly by one link connected to anything else. So now I move on to C. We've already established C is with B and A. Does C go with anyone else unique? Who? This is Mickey Mouse. Don't tell me this is hard. All right? And then does C go to anyone else directly? Yes or no? No. Then what does that leave D? Does D go to E? Yes or no? Because we already know D goes all. We already established what D is connected to A through C. We're missing one. Does anyone know? Hold up. There's one more. Who is E connected to? Who's E connected to? We already have that established. Boom. Why is E connected to E? This is a what? Loop. Wasn't that fun? So E is connected to itself. That's a loop. I just showed you. Go. What's everyone yelling for? I said it was right here. Loop. Look. Come on. That's a loop. What are you doing?
Why does he always turn around so dramatically? Just interesting.
Okay. Now this one is, okay, here's the question. This one I'm just going to shove right at you. Okay, so the answer I'm going to show is some possible answers you would have. Let me have you read it first. Draw two different graphs such that the pairs listed are adjacent. ADJ. So you have to draw that A is adjacent to B. A is adjacent to C, and so on and so on and so forth. Okay, write that down. Here's the answer. Oh, it's still frozen. All right, let's take our time. There we go. Now the class is revealed. Whoa! Okay, so what I wanted was the connections. Okay, now listen. This everyone's picture would definitely look different. Why did I put A in the upper left? I don't know. Could you have put A in the lower right part of your page? Yes. All you need to do is have a line connecting A to who first? B. So let's go ahead and erase this and then go in order how this graph through tick marks was created. So again, it'd be a pain in the behind for me to grade this because every graph will definitely look different. Because where are you going to put everything as far as where the letters are concerned? So I start by putting A here, and I draw a line A to B. There's a direct connection. Then I got to go on my page and put C anywhere. I can put C up here. I can put C here. I can put C here, here. You get the point. It doesn't matter where you put C. The decision was to put C here. And then I had to draw a line to it. And I don't care how long the line is or how short it is. It doesn't matter. That's why there's an infinite amount of ways this could be drawn. And then A to E. There's a direct connection to those two. What's B to B mean? Now we know. It's a loop. So I've already had B drawn. Now I got to draw a loop to it. And I just circle B because it's my favorite letter. So B to B is gone. Then C was already drawn. You could draw, these don't have to be lines. They could be little squigglies. It doesn't matter. I could do a loop, not a loop, incorrect word. But you can draw any way to show that connection. Doesn't have to be a line. I'm not saying straight line because that's like saying a female girl and a male boy. All lines are what? Straight. Redundancies. Don't like them. So B to C is done. Now, D was not created yet. So I could put D here, 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 here. I decided to put D there. And then I drew a line to D. Is this a vertex, yes or no? No. The more letters, it's almost impossible not to have crossings. These are bridges. They don't cross each other. It's wrong to say that they cross. They don't, technically, in this little scenario. And then I did not have E. And then I have to draw E and then connect it. And then the last thing I have to do is C and D were already drawn, so I just have to draw a line to them. I did not hit that. Or you could do this. All right, and I guess I could zoom back. In all of your drawings, you could draw your points as a straight listing of the coordinates. Just put A, B, C, D, E. Just put them down in order, straight across, with some space. And then here's A to B. Done. Now, this is not A to C. What does that path mean? A to B, then B to C. So for me to draw A to B, now I need some curves. So there's A to C. That is a direct link, not going through B to get to C. So that's what we have to make sure we understand. Then this is not A to E. This is A to B, B to C, C to D, D to E. That is a long progression. The only way to draw A to E is a direct curve situation like this. And so on and so on and so forth. So there's A to E. There's B to B. Just marking off what's been listed here. I do need a direct link from B to C, so that is that one. I do need a direct link from B to D. This is not B to D. That's B hitting C, then C going to D. And hopefully you taught about the computer aspect of this. It's not a direct link. You had to hit a hub first before you went there. So the way to draw that is this one maybe. All right. And then B to E, which is this one. And then C to D, since I've listed it like this, that's the last one. All right. Now, there's really only a little bit of math as far as numbers are involved. And I'm not going to derive this formula that is coming up. But before we come up, we got to talk about degree. And it's just a term for these little mappings. The degree of a vertex just equals the number of edges that come from that vertex. Now, this is what blew my mind, and your book just stated this and didn't explain it. Whenever you have a loop on a singular point, that actually equals degree 2. What? So the next thing I did is I went to Wikipedia and looked up graph theory, and then in graph theory I looked up loop. And then I pulled this out and put it on our thing. But you can actually find it in the same web page by hitting loop on that link in there. For an undirected graph, the degree of a vertex, just what I just said right here, is equal to the number of adjacent vertices which are connected by an edge. So same terminology. Special case is a loop. Here we go again, which adds 2 to the degree. Why? Well, they go further and explain it a little bit, and you may or may not understand it. I'm not saying I understand it, but at least I know why we get a 2 on this. This can be understood by letting each connection of the loop edge count as its own adjacent vertex. In other words, a vertex with a loop sees itself as an adjacent vertex, from both ends of the edge, thus adding 2. The best way that they say this is going in and then going back out to itself. Loop and loop. So that's why it counts it as 2 edges. Very strange. So now this last example, which I'm going to zoom back, and I don't care which one you look at, the first or the second, how many edges does A have? Well, actually, you can look at the list. A goes to B, A goes to C, and A goes to E. So what is that? 3. You can actually just look at the listing. You don't have to look at the picture. It's one or the other. Now, B is a little strange. B goes to C, D, E, and A. So that's 4, right? But then what does B go to B? What does that add to it? 2. So that's why B has a degree 6. So loops count as 2 for degree. But it is only one edge there. We're just talking about the degree of it. And I jacked that up first hour when we did the next thing. You don't need to know about that. C, if you look at the picture, C has 3 things. C goes to B, D, and A. So that's degree 3. And then so on and so forth. D has 2 edges, and so does E. All right. Now, that's not really math except counting. We counted. So there's the numbers. Here's the math. It's a formula. And basically, somebody came up with it, and I'm just going to accept it. I like to give you formulas and tell you where they come from. I guess I'm not doing that today. I don't know. Here's a formula. The sum of the degree of some sort of situation like this, some sort of routing situation that we have graphed on a paper, will always, formulas are always true in all conditions, equal twice the number of edges. Wild. Memorize. That's your job. There is no I don't get it. There is you don't have it memorized yet. All right. So first of all, what's 3 plus 6? 9 plus 3? 12 plus 2? 2 plus 14. 16 is the sum of the degrees, or the degree. I hate when that goes off because it's awkwardly silent now. Now, let's count the edges. This is what I jacked up with the other hour. I counted this as 2 edges because I had 2 in my head for loops. How many edges is this thing? That's 1 edge. This is 2 edges. This is 3 edges. 4, 5, 6, 7, 8. Who do we appreciate? What's 2 times 8? 16. So 2 times the amount of edges equaled the sum of the degrees. So that's what this formula means, and it worked for this situation. It would work for all. All right. Uh-oh. I just started the movie. Okay.
A loop is
1 edge, but it's considered degree 2 because it loops there and back, I guess, is how that Wikipedia described it. So that's why it's counted as 2 edges. That's degree 2. Degree 2. 1 edge, though. Oh, I am moving. It is going. Whoops. All right. Then here's the last thing. What? This is the last one, though, folks. We're fine. Okay, go ahead and take this down, and then we'll explain it. A path in a graph, or a path in a networking situation. I'm trying to talk about our computer situation. A route that passes from one vertex to another. So the point of your computer is a point. The hub in the class is a point. The tech office has something in there that connects to our hubs. And then they go out to the world, and there's billions of hubs after that, how things are connected. So path in a graph. Rules that hopefully are actually shouldn't have to be written. So don't overdo these 4 things. And there are a couple rules that you might, though. So obviously from starting at point A, where does point A have to go in this little linkage? It could either go to who? C or B or E. So the first one, each vertex must be adjacent to the next vertex used to start the linkage. You have only one link right now with your Chromebook, and that's our hub in our classroom. There's only one possibility out of this room. If that hub breaks, you have no internet, you have no choices, unless you get your phone out and turn it into a Wi-Fi, right? Now that it's illegal, you'll get busted immediately, especially in this class. Officer Samuelis. Watching, all right? Yeah, that's opening up another hub or another link. Anyway, I love it. 2, or the second one, each edge is used at most once. So you're not going to use an edge twice, but you're going to see some silly stuff that's going to happen. Like the third one's kind of silly. Vertices can be used more than once because vertices can be connected by more than one edge. Would be a strange situation to do that, but that's it. And then all you do is write this as a list of vertices. So we're going to write some paths. So here's your example. This is what you'd have to do in your homework, let's say. Okay, here's the picture given. Give me some paths from A to G. Maybe I'll say give me 3 of them. Now, what I could do, I told this 5th hour, I could make this multiple choice question. What are all legitimate paths from A to G? Choose all that apply. Oh, I love it. It's a great idea. Because if I left this out to the open, I'd have to grade all of your work, and all you guys would be like have different probably paths. But most of us would probably pick the most direct. Now I'm going to circle A and G. Those are not loops. I'm saying I have to get from A to G. What's the fastest? I started A. What do you think I could go next? I don't think E would be the next fast. C. So A goes to C, and then what? C goes to G. Are these vertices right here, yes or no? No. Done. So that's one path, and that's probably the most direct path. Okay, I said give me 3 different paths. So what could I do next? Maybe A to E. This requires some more points, though. Where would I have to go next? I guess you have some choices. E would go to what next? D, or, this is what I mean about answers may what? Vary. And it varies probably with what I did first hour. Then D goes to what? G, if you want to get this done. You could have said D goes to F, and then F goes to G. That would have been a legitimate possible path. So that's all you're doing. You're looking at possible paths. Some are more efficient than others. Let's do the worst one possible ever. A goes to who? B. So A goes to B. Then who does B go? C has to go to C. Then this is crazy. C is allowed to go back to what? A, because that is an edge used once and only once. Vertices can be used more than once. So that's the rules in the path of this. And then we have some options. Actually, we don't. Where do we have to go next? Have to go to E according to this thing. Now we have some options. Let's do something different. Let's go E to F this time. Then, just to make this really hard and make it longer than it needs to be, F goes to who? D, because we want to make this as long as possible. And then D has to go to G at the end. D couldn't go to E because then we'd be stuck. We'd have to reuse an edge. So this has to be the end. 3 different ways to get from A to G in this routing pattern, okay, of how things are connected. Oh, here's your homework. Boom. Like I told somebody last hour, what's the page? And I go, find it. Be Scooby-Doo. Oh, that's a terrible Scooby-Doo. That almost sounded like Yoda. For the love of dog, you can find the page number. Just open up to section 6.1 and see where 1 through 11 starts. Hey, have a good day.